review for our finals here about chemical bonds. If you remember, chemical bonds is just a force of that holds groups or two or more atoms together and makes them act as a new unit. It could be a compound, a molecule, whatever. The big two we talked about a lot this year were ionic and covalent, and we'll go over those again in this little review. Super important, the reason that elements bond and form bonds is the octet rule. Atoms will gain, lose, or share electrons, whatever they need to do, in order to get a full set of valence electrons, that outer level. We know that octet means 8, so we want to get 8 in that outer level, at least when we're talking about the orbitals, which we're not going to here. Just realize we do need that full energy level, outer energy level with our valence electrons full, and that's why you're going to form bonds if you're an atom. If you gain or lose an electrons, that's an ion. If you gain an electron, you've gained a negative, so you're a negative ion. If you lose an electron, you've lost a negative, so now you're positive, you'd be a positive ion. When you share electrons, we had said that would be covalent bonding. But either way you do it, gain, lose, or share, you're doing it to get an outer energy level. Hopefully you remember the cheat code here. How many valence electrons? If you're in the first group, group 1 has 1 valence, so all of these have 1 valence. Move over, they all have 2. Skip over to 13. Remember, the transition metals are weird. We'll go over that when we go over naming. 13 ends with a 3, so they have 3 valence, 4 for 14, 15 has 5, 16, 6, 17, 7, and 18, 8. So it's real easy. It might even be written on your own periodic table throughout the year. Makes it so you don't have to figure out how many electrons are in the outer shell for everything. You can just look at a periodic table. All right, ionic bondings. These are the ones when atoms lose or gain electrons. If you lose an electron, you've lost a negative, you become positive. So if we look here, the valence electron shown here, there's only 1. So if we lose this one, the level below it is already full. So we lost a negative, so this would become positive. Where would it go? It would go over here because they need 1 to have a full octet. If we draw this here, now they have 8. But they have an extra negative electron, so they would be negatively charged. Positive and negatives are opposite charges, and they attract. So that's what actually holds them together, that electrostatic force. And that's what I said on the other one. This is just another picture. If you want to pause it and look at it a little neater than I had it, feel free. And pause here to put all this in your notes. A little more on ionic bonds. Remember, we said electrons are transferred from one atom to another because one needs to lose an electron or more than one to fill their octet. Another atom needs to gain 1 or more to fill an octet, so that's why they're transferred. Cations are attracted to anions. Remember the vocab. An for anions means a negative. So anions are negatives. They're ions that have gained electrons because now they're negative. Cations are the positive ones. Ionic bonds are also formed between a metal and a non-metal. So we're talking about stuff from the left side of the periodic table, the metals, combined with stuff from basically groups 14 through 17, the right side, the non-metals. The left side form cations because they need to lose electrons, so they're going to be positive. The non-metals, the right side, want to gain electrons, so they're going to form anions, becoming negative. What do ionic compounds have in common with each other? They all have high melting points. They're brittle, meaning they're easy to break. They're usually salts as well. Most of them dissolve in water, and they can conduct electricity because those ions are charged, and they can separate and then move that electricity or those electrons along. We'll go over this one again here. This one shows all of the electrons. The only ones that matter, though, are on the outside. So sodium has 1 valence electron. If we count chlorine, 1, 2, 3, 4, 5, 6, 7 on the outside. Well, if we lose this, now the outer level is that one, which already has 8, full octet. So it's going to lose this electron, but it lost a negative, so it becomes positively charged. This has 7, so it says, hey, I'll take that. I'll add that to my outer level to complete my octet, but I've added a negative, so now I have a negative charge. That's what they show at the bottom. Positive charge, negative charge, opposite charges attract. That's what holds those bonds together. Go ahead and pause while you put that last bit of information about ionic bonds into your notes. And then, once you have that, we'll move on to covalent bonds. Remember, we hinted at it at the beginning of this and said that's when they share electrons. So what happens here is both elements or both atoms need to gain electrons, so they need to share them. And this is going to happen between nonmetals. So two things on the right side, which makes sense because we said things on the right, the nonmetals need to gain electrons, so both of them need to gain them. So that's why they're going to form covalent bonds. They're going to share. If we look down here, we have chlorine and chlorine. So two chlorine atoms. Each of them have 7 valence electrons. So this one's not going to lose an electron because then it has 6. Well, that's further away from the 8 it wants. So that's not going to work. This one doesn't want to lose one because then it would have 6 and it's further away. But what can happen is when their clouds get close enough, they can share electrons. So it counts for both of them. And in that case, they would have a complete octet. If you look here, we have oxygen. Only have 6 valence electrons, so they would need to share 2 pair, and that's all right. If you remember, if you see a picture that has a bond connecting something in the Lewis dot structure, it represents 2 electrons. So when we look here, oxygen has 1, 2, 3, 4. This line here counts as 2, so that's 6. This line counts as 2, so that's 8. We already said that's 2, 4, 5, 6, 7, 8. So they both need to gain, so they share. And you can even share 3 pairs like nitrogen does. What properties do covalent bonds have? They have low melting points. Well, that's the opposite of ionic. They're soft and flexible. That's the opposite of brittle. So they're not easy to break. So again, the opposite of ionic. And most of them don't dissolve in water and they can't conduct electricity. So really, if you just remember the properties of ionic, covalent will be the opposite of that. Go ahead and pause while you throw all of that into your notes. Then the weird ones. They're not weird in reality, but they're the less common ones, the ones we don't spend as much time on. Metallic bonding, hydrogen bonding, and polar covalent bonds. Metallic bonds are, they're easy because they form between metals. So what happens is there's an attraction between the positive nucleus of one metal ion and the electrons around them from other atoms. So it's still opposites attracting, but it's not ionic because the electrons kind of move freely, like you'll see in the next slide's picture, between all the metal atoms. But that's why they're such good elements at conducting electricity and heat, and even allows them to be flexible. Here's kind of picture I was talking about. All of these A listed atoms are metals, and they're positive in the nucleus, and these blue things are electrons, but they're attracted to all of them. They're just kind of sharing them throughout. They're just attracted because the positive nucleus attracts the negative electrons of others, but that's free-moving electrons, which really is what electricity is. Polar covalent. That's really right there, the big words. Unequal sharing of electrons. So it's still covalent, so it's still sharing, except things aren't shared equally. If we look at this picture, fluorine's a much bigger, so it would have more mass, molecule, or atom, which means it's going to take the shared electrons more often. It's going to kind of use them up, be greedy. It's going to take them more often, and that's all the unequal. They do share them. Fluorine and hydrogen will share a pair of electrons, but those electrons spend more time around the bigger fluorine than the hydrogen. So that's what polar covalent is. If you see this symbol here, it's a Greek symbol. It just means partial positive. In other words, it means those don't have the electrons as much, so they're slightly positive, and the ones that are slightly negative, the bigger atoms, fluorine, get those electrons a little more. I'm going to let you watch this to kind of refresh your memory.
Let's look at hydrogen atoms that bond with an oxygen atom. These atoms are sharing electrons, which makes this a covalent bond. But here's the thing. Oxygen has 8 protons in the nucleus, and each hydrogen only has 1 pathetic proton in their nuclei. The ability for oxygen to attract the electrons is stronger than hydrogen's ability. This is known as electronegativity, but I think of it as electron bullying because oxygen is going to have the electrons around its nucleus more often than the hydrogens have the electrons around theirs. As a result, the oxygen side becomes slightly negative and the hydrogens become slightly positive. This is an example of a polar covalent compound. The positive and negative ends create poles, like the ends of a magnet. But not all compounds have this kind of relationship. On the spectrum of bond polarity, non-polar covalent bonds share electrons very equally and don't create poles. Polar covalent bonds share electrons unequally and create dipoles, which also cause some intermolecular attractions. And ionic bonds are so polar that the electrons are actually transferred to the more electronegative element, and their charges attract them to one another, forming an ionic bond. Let's look at some examples of the covalent bonds. Non-polar covalent bonds share electrons equally. Examples include all of the Brinkelhoff twins, like nitrogen and oxygen and fluorine, but also other molecules like carbon dioxide that have atoms with really similar electronegativities. Polar covalent bonds, or just polar bonds, have bonding electrons that are shared unequally, like hydrogen chloride, which is also called hydrochloric acid. The chlorine atom attracts the electrons more than the hydrogen atom, so the chlorine becomes slightly negative and the hydrogen slightly positive. We can symbolize this partial charge with the Greek letter delta. Fluorine gets a partial negative and hydrogen gets the partial positive. One of the most important polar molecules for life is water. These water molecules prefer to have opposite ends near each other. The slightly negative oxygen ends are near the slightly positive hydrogen end. The polarity of water makes it great at dissolving lots of different substances that are also polar. The water molecules have slight attractions to each other, and even to other molecules. These attractions between molecules are called intermolecular forces, and they are much weaker than either ionic or covalent bonds.
And that's the most important part of that little clip. Go ahead and pause while you put this into your notes. All right, as they mentioned in there, electronegativity, when different nonmetals form covalent bonds, they almost never share the electrons equally. Remember, one molecule is bigger, more massive, so it's going to get a little bit more of the electrons around it, which makes it partially negative, versus the smaller one that's partially positive. That's called electronegativity, and that's the relative ability of an atom to attract the elements to itself. If you look at this periodic table, these numbers, the bigger the number, the more electronegative an element is, meaning the more it's going to hog those electrons, like the video said. So, if you just remember, start at fluorine, it's the most electronegative. As you go to the left, electronegativity gets smaller. As you go down the periodic table, it also gets smaller. Hydrogen bonds. They mentioned this a little in the video as well. They're called a dipole attraction between a hydrogen and a covalent bonded, very electronegative atom like nitrogen, oxygen, or our big one, fluorine there. In this case, the molecules actually end up having a partial positive side and a partial negative side, as we said. And basically, what you need to remember, no matter what we're talking about, the biggest key is covalent, ionic, hydrogen. It doesn't matter. Any of these ones we've talked about, the whole point is to try to get that complete octet, like noble gases already have, and that's the whole reason behind bonding. Go ahead and copy this into your notes, and then you can do your Kahoot review.